Okay, what I have on the board is pretty much a summary of what we did this morning in class, bringing us up to speed on this concept of equilibrium and equilibrium constant. This is just a generic, fictional, hypothetical chemical reaction, A plus B reactants, go to C plus D products. And remember, all reactions are reversible, no exceptions. They go forward, they also go backwards. It's just a matter of degree, how far backwards. But every reaction will have an equilibrium constant. Well, I should back up further than that. Remember that every reaction is either at equilibrium or on its way to equilibrium. And that goes for anything, a piece of chalk, a piece of cheese, a glass of water, a chemical reaction. Everything in the physical universe is either in its equilibrium state or it's moving towards its equilibrium state. And you can think of equilibrium as being home, like a position of rest, a position of permanence, a destination. So this reaction is heading towards equilibrium. When it gets to equilibrium, there will be an equilibrium constant that describes that particular equilibrium state. And the equilibrium constant, if you recall, is simply the concentration of the products divided by the concentration of the reactants. That's broadly or generally stating. The exact or specific form of the equilibrium constant is what we have here. It'll be the concentrations of each product species raised to a power equal to its stoichiometric coefficient divided by the concentrations of the reactants. Each of those reactant concentrations raised to a power equal to their stoichiometric coefficients. So that's the equilibrium constant. And the equilibrium constant will have a specific value for a given chemical reaction at a particular temperature. And it'll always have that value. It's reproducible, regardless of how the reaction got to equilibrium, regardless of where it started, regardless of whatever else may be happening within that system where that chemical reaction is doing its thing. This K value will always have that specific value. It's equilibrium constant value. Now we talked about the fact that that equilibrium constant value has a range of possibilities, and the range goes from 0 up to infinity. And keeping in mind that the K, or the equilibrium constant, is the concentration of products over reactants, the minimum value, the smallest value of the equilibrium constant is 0. And what does that mean physically? That means we don't have any product, right? Product concentration is 0. All of the reaction is in the reactant form, right? The reaction is shifted all the way to reactant at equilibrium. That would be K equals 0. The far extreme, so that's the minimum value. The maximum value would be K is equal to infinity. And that would be when the reaction is shifted all the way towards product. There's no reactant present and only product, and any number divided through by 0, which would be the concentrations of the reactants, is going to be infinity. So that's K is equal to infinity. All product, no reactant. And all reactions fall somewhere within that span, that range. And as we talked about in class this morning, if you have a chemical reaction, look at this one first. What does it mean physically if the equilibrium constant has a value of 1.0? Keeping in mind that it'll always be the concentration of products over the concentration of reactants. If that's equal to 1, that must mean that we have equal amounts of reactants and products, correct?
Correct.
So that would be K equal 1. I've never seen of a chemical reaction that has an equilibrium constant of 1. Could be, I'm sure there is one somewhere, I just haven't seen one. But anyway, what if K is much, much less than 1.0? What does that say about the system, the chemical reaction at equilibrium? What's it going to look like physically if its equilibrium constant is really, really, really tiny?
The
Reactants dominate. Right? If this is really tiny, that's because we have a lot of reactant at equilibrium and hardly any product. So that would give us a small value. We say that the reaction equilibrium is shifted to the left or lies far to the left. Left being left side of the reaction arrow, shifted towards reactants. What if the equilibrium constant for a different reaction is much, much greater than 1.0? What does that tell us about this reaction at equilibrium? What's it saying? Saying that if the equilibrium constant is concentration of products over reactants and it's a huge number, that means we have a lot of product at equilibrium and hardly any reactant, correct? And technically, or in terms of vocabulary, we say that products dominate, and we say that the equilibrium is shifted or lies far to the right, far towards products. Okay. Okay. Sound familiar? All right. So here are a few reactions. Nitrogen reacting with hydrogen to form ammonia. The equilibrium constant is 3.8 times 10 to the fourth power. What can we say about this chemical reaction once it's achieved equilibrium? Once it's completed its chemical journey, it's at home, it's at rest, it's where it wants to be at equilibrium. What are we going to have more of in that system? Product or reactant? Product. Right? That's a big number. That's much greater than 1. Products will dominate. We're going to have a lot of ammonia and just a little bit of hydrogen and nitrogen at equilibrium. Okay. What about this reaction? Hydrogen gas reacting with oxygen gas to form water. We did this reaction in class a few weeks ago. Remember the hydrogen balloon? Boom, in a millisecond, the reaction was complete. Where did that reaction end up in its equilibrium state? Its equilibrium constant is 10 to the 42nd power. That's a big number, right? 10 to the 23rd, that's Avogadro's number, 6 times 10 to the 23rd. That's a huge number. This is what, 20 magnitudes greater than that. Therefore, this is a huge number. The equilibrium is shifted far to the right. Good luck finding even one oxygen molecule or hydrogen molecule at equilibrium. The reaction is so far shifted towards the products. All right, here's a third example. Calcium oxide decomposes into calcium and oxygen, and the equilibrium constant for this is 10 to the negative 11. So at equilibrium, where does the equilibrium lie? Towards reactants or product? Reactants, right? It's shifted far to the left. At equilibrium, you're going to have a lot of calcium oxide and very little calcium or oxygen gas. So that's that stuff. Any questions on that? These are things we talked about this morning. I have my eraser.
Oh, okay.
Yeah. No questions, comments, clears? Longer? Okay. So let's move forward, onward and forward. And let's look at this chemical reaction. What's the name of that ionic compound? What is it?
Fluoride? No.
Nope.
Fluoride?
Nope. Calcium carbonate. Excuse me. Sorry. Chalk dust. Calcium carbonate. Solid. So the calcium carbonate decomposes into calcium oxide and solid and carbon dioxide. And as an equilibrium constant, its value is infinity itself. So where's the equilibrium shifted for this chemical reaction? Towards reactant, right? What are we going to have more of, reactant or product at equilibrium? Much less than one, we have a lot of that. And a straightforward application of the writing out of the equilibrium constant would give us that. That seem appropriate based on what we've said so far. Product concentrations over reactant concentrations, each raised to a power equal to its stoichiometric coefficient. That seems appropriate. It's not right, it's wrong. But not because it's any different than anything we've said so far in terms of how to write those out. There's a new thing that we have to introduce here, and that is, notice that the calcium carbonate is a pure solid, and the calcium oxide is a pure solid. And it turns out that we do not put into the equilibrium constant pure solids or pure liquids. We only include into the equilibrium constant those reactants and products whose concentrations change as their amounts change, as the reaction proceeds. And it turns out that a pure solid or pure liquid, its concentration does not change as we change the amount of it that we have, which kind of seems counterintuitive. Think about this. Let's say I have a piece of chalk. Let's say I have 10 grams of chalk, of calcium carbonate. And what is the concentration of that calcium carbonate? Well, I've done the calculation earlier, and it turns out that the concentration in moles per liter of calcium carbonate is 27 moles per liter. So that is, I have this 10 grams of chalk. The concentration is 27 moles per liter. Now what happens if I have 5 grams of chalk? What's the concentration? It's still 27 moles per liter. What if I have 1 gram of chalk? What's its concentration? 27 moles per liter. What if I have the tiniest little speck of chalk dust? What's the concentration of that tiny speck? 27 moles per liter. Right? And that's true for any pure solid. The concentration, as long as the temperature and pressure remain the same, the concentration does not change regardless of how much you have. Whether you have 100 grams or 10 grams or a half a gram, the concentration of a pure solid will always have the same value. And we don't put that into the equilibrium constant. We only include into the equilibrium constant those things, those reactants and products whose concentration will change as the amount of them in the reaction changes. Another example, pure water. So we don't include pure solids or pure liquids. Let's go ahead and write this out. So the true form of this equilibrium constant is going to be eliminating the pure solids, and it'll end up being that. That is the equilibrium constant for this chemical reaction. That's gas. So anything that has a solid subscript, indicating it being a pure solid, or a liquid subscript, indicating it's a pure liquid, will be omitted from the equilibrium constant. But if it has a gaseous, a G, as a subscript, or if it's in solution, like an aqueous solution, part of the mixture, these do go into the equilibrium constant. These are omitted from the equilibrium constant. That makes sense? Okay. Let's look at this idea of pure water. Here I have 100 milliliters of pure water. So I have H2O liquid. What is the concentration of that water? And it turns out that 1 gram of water, the density, write it that way. The density of water is equal to 1 gram per milliliter. Right? That makes sense? If we have 1,000 grams of water, 1,000 milliliters of water, correct? 1,000 milliliters is equal to 1 liter. So we have 1,000 grams of water. Convert the grams of water into number of moles. There is 1 mole of water for every 18 grams. And you come up with 55.6 moles per liter. That's the concentration of water. Okay. So I have 100 mils of water. Its concentration is 55.6 moles per liter. Now I have 50 mils. What's its concentration? 55.6 moles per liter. Now I have 20 mils, 55.6 moles per liter. Now I have a drop. What's the concentration of that drop? 55.6 moles per liter. So for any pure liquid or pure solid, the concentration remains constant regardless of how much you have. And therefore, we do not put them into the equilibrium constant. We only put into the equilibrium constant those reactants and products whose concentration literally changes as the reaction moves towards equilibrium, as the amount of that substance, that reactant or product changes. Make sense? Let's look at another example. Let's say, it's a chemical reaction. And it's actually the dissociation of acetic acid. This is acetic acid. And what would the form of the equilibrium constant be for this reaction? What do we plug in and what do we leave out? Would we would that go in? Yes. Would this go in? Yeah. Would that go in? Yes. Would that go in? No. So that would be the equilibrium constant for that balance equation. Okay. It may seem like it's straining at a little detail, but it's the difference between having the right value and the wrong value and making the problem come out correctly versus. Okay, so that's that. Any questions on this? If anybody ever asks you what the concentration of powder is, 55.6 moles per liter. Kind of a weird question, but it could show up on a test. I like that. Being able to convert that into a concentration using that kind of approach. Okay, so that's that. And now we're done for the meantime with respect to describing the characteristics, the properties of the equilibrium constant. Now what we're going to do is actually use the equilibrium constant to solve problems, because that's why we like it. It's a powerful tool for giving us information for measuring the properties of chemical reactions. And that's what we're going to look at now. Application of equilibrium constant. If we have a chemical reaction and we know the value of its equilibrium constant, what can we do with that? What can it tell us about a chemical reaction? And there's two things in particular right now. There's more than that, but right now we're going to look at two things that the knowledge of the value of the equilibrium constant can tell us about a chemical reaction. And one would be the direction of the reaction. And the other would be the concentration of reactant and product species at equilibrium. So we're going to look at both of these now. So number one, the direction of a reaction. In order to use the equilibrium constant to predict which direction a reaction will have to go to get to equilibrium. And remember that statement earlier today? A chemical reaction, any reaction always goes in the same direction. It'll always go in the direction towards its equilibrium position, right? Remember that. So how can we use this to determine the direction? In order to do that, we need to introduce a new term, and that term is Q. And that's called the reaction quotient. And what on earth is a reaction quotient? I should write that out. Let's go back to a generic chemical reaction to demonstrate this. A plus B reacts to form C plus D. And let's say that these are all in the gas state. We don't have any pure liquids or pure solids here. And what would be the form of the equilibrium constant for this chemical reaction? It's going to be concentrations of products over concentrations of reactants. Each raised to a power equal to the stoichiometric coefficient, correct? Now, what is this idea of Q? That's the equilibrium constant. What is this reaction quotient? And this is what it is. The reaction quotient has exactly the same form as the equilibrium constant with one important exception. And what is the important exception or difference between the equilibrium constant and the reaction quotient? I'm sorry? I can't hear you.
It has like a sign of the polarity to look after the value of K.
No? What did the little subscript zero
The
mean? Initial. Right? This is the set of initial reactant and product concentrations. This is where you start. And this would be the exact form of the equilibrium constant, but we don't plug in the equilibrium concentrations of products and reactants. We plug in the concentrations of what we have now, what we are dealing with, what we currently see. And that would be the reaction quotient. Now, let's say we do that for a given chemical reaction. And let's say that Q is equal to K. What can we say for sure about that particular set of concentrations that are plugged into that Q value? They represent equilibrium, right? If Q, the reaction quotient, equals the equilibrium constant, we're at equilibrium. We're home, we're at rest, the reaction is where it wants to be. That's if Q is equal to K. But what if Q is greater than the equilibrium constant? What does that mean physically? That would mean that we have too much product in the system, right? Both of these are product concentrations over the reactant concentrations. If Q is larger than the equilibrium constant, then we must have too much product. Does that make sense? So what must the reaction do to get back to equilibrium? In which direction will it have to run in order to get to a value that's equal to K?
Reverse.
What's that?
Reverse.
Reverse, exactly. The reaction direction will be from product to reactant. The reaction will have to run in reverse and consume some of the extra product we have and make more reactant. And it'll keep going this way, keep going that way until we get a set of concentrations that will make Q equal to K, and then it stops. Then we're at equilibrium. Okay. What if Q is less than K? What does that mean physically? We have too much reactant, right? The Q value is too small because we don't have enough product. We have too much reactant. So back up here, we could say we have too much product in our system at time 0, where we currently are. And so to get to equilibrium, the reaction is going to have to run in a direction that will consume some of that product and lower the value of Q to get back to equilibrium. And the reaction runs in reverse. But now we have too much reactant. If the Q is less than K, or you could say not enough product, right? It's the same thing. So which direction must the reaction run to get to equilibrium? This reaction quotient is less than the equilibrium constant value. It's going to have to go forward. That's going to be the reaction direction. It'll go forward, and what it'll do will consume reactant and produce more product, and it'll keep going that direction until we get a set of concentrations that will give a value that's equal to the equilibrium constant.
So in order to make these comparisons, we have to have both Q and K. We can't just work with just K.
That's right. You have to know what K is. If you know the value of K, then any particular combination of reactant product concentrations you put together, you can evaluate it and determine which direction that reaction will have to run to get to equilibrium. Okay. Make sense? All right, let's look at an example. Let's say we have nitrogen gas reacting with hydrogen gas, form ammonia gas. And say the case, the equilibrium constant for this reaction is 0.060, which is equal to 10 to the 6 times -2. And say that that's at 100 degrees C. So remember, every chemical reaction has a unique value for its equilibrium constant at a given temperature. If the temperature changes, the value of its equilibrium constant changes. But for this reaction, if it's at 500 degrees, its equilibrium constant will be 6 times 10 to the negative 2. So let's say we have a set of concentrations that we throw together in the lab. These are going to be initial concentrations, what we currently have, right? Little subscript 0 times 0, where we are right now in time. And let's say that the ammonia has a concentration of 0.001 mole per liter. And the nitrogen is 0.00001 mole per liter. And the hydrogen concentration is 0.002 mole per liter. And you're asked, which direction is this reaction going to run, given these concentrations of reactants and products? And how do you determine that? You calculate Q, right? And compare the value of Q with these concentrations with the known value of the equilibrium constant. So we'll calculate Q, and of course is and initial concentrations. So the ammonia, NH3, 0.001 mole per liter. Don't forget to square it. Divided by the concentration of nitrogen, 0.00001 to the first power, divided by the initial concentration of the hydrogen, which is 0.002 to the third power, right? Third power, because its coefficient is 3. So you take out your calculator, you do the appropriate button pushing, and you get a value of 1.25. Which direction is this reaction going to run? Or is it at equilibrium already? Definitely not at equilibrium. We've got to compare Q and K. K is 0.06, and this is 1.25 times 10 to the 7th. This is 12.5 million, and that is 0.006. So Q is much greater than the equilibrium constant, meaning we have too much of what in our reaction system? Product. Okay. Product over reactants, we have too much product. Q is way too big. So which direction does the reaction have to go in order to get back to equilibrium? Has to go that way. Exactly. And it's going to have to go a long way in that way, right? Because we're at 10 to the 7th, and we got to get all the way to 0.06. So the reaction has to run and consume a lot of that product to get back to equilibrium. So the reaction direction is towards the reactant. Once this reaction does get to equilibrium, what's favored of equilibrium? What are you going to have more of, product or reactant at equilibrium? K is less than 1. That means we have more reactant than we do product in the system. Yes. At equilibrium, you're going to have more of these guys than you are that. How do we know that? Just because its K value, its equilibrium constant is less than 1. And remember, I said, always keep in mind that in general, all the equilibrium constant is doing is giving us the ratio of the concentrations of product to the concentration of reactants that will be in the system at equilibrium. And if it's greater than 1, that means we have more product than reactant. If it's less than 1, then at equilibrium, we're going to have more reactant. So that's this guy, the equilibrium would lie towards the left, right? Lie towards reactant, meaning reactants dominate in terms of the amount present. Questions, comments? Yes. Oh,
So like question two, part A asks about the concentration at equilibrium. Would it be false because, like you said, hypothetically it could be equal, but it would be very rare for it to be equal?
what were you referring to?
The first question.
Oh, yeah. At equilibrium, the total concentration of products and reactants is equal. It could be, but very unlikely. I've never seen a reaction who has a K value of 1. That would mean you have equal amounts.
So you're looking for false.
What you can, yeah, A would be false. What you can say that is true is that the concentration of reactants and products remain constant with time, right? They don't change. And that the rate of the forward reaction is going to be equal to the rate of the reverse reaction. That's true for any chemical system at equilibrium. But you're right, that would be false. He's talking about, oh, you don't even have this yet. I'm going to hand this out at the end. And this is going to be the assignment that you turn in next week. It's 8 questions, all involving equilibrium, the kinds of things we've been talking about. And you'll turn this in next week and it'll be worth 25 points, like a lab report. But we'll talk more about that later. But Bull pointed out that question 2 is true, has a set of true false statements, and letter A is false. Because, well, we'll talk about it later. Any questions on this? So we can use a knowledge of the equilibrium constant value to determine which direction a reaction will have to go to get to equilibrium when a particular set of concentrations are present. Does that make sense? That's what we were just showing. Okay, now, the second thing, important thing that we can do, given a knowledge of the equilibrium constant for a chemical reaction, is to using Q, knowing the value of the equilibrium constant, we can determine the direction of a reaction, and we can use it to determine concentrations of each reactant or species of equilibrium. So that's what we're going to look at now. We've done the direction of the reaction using that reaction quotient term that we introduced. Now we're going to look at doing calculations that will allow us to determine, to predict in advance what the concentration of each reactant and product species concentration must be. And okay, that's a typical problem. Calculating equilibrium concentrations. It involves mixing a set of reactant and product concentrations and then asking, once this system gets to equilibrium, how much reactant will be present, how much product will be present. That is, given a set of initial conditions, initial concentrations, how much product, what will be the concentration of product in that system at equilibrium. And these kinds of calculations can get pretty complex, and therefore you should use a standardized approach so you don't paint yourself into a corner that you can't get out of. And I gave you this in class today. It's the 7 steps to success for calculating the equilibrium concentrations of reactants and products in a chemical system. Does everybody have this? Does anyone need one? Those don't have to use these steps. I've done this before a lot of times, as long as you got to use the structured approach. Make your life easier and to come up with the right answer. So we're going to do an example. We're going to calculate the equilibrium concentrations of reactant and product for a chemical reaction. And here is the reaction. Let's say we have hydrogen gas reacting with fluorine gas to produce hydrogen fluoride gas. And we know the equilibrium constant value for this reaction. That has to be given. Remember, what we're doing is applying a knowledge of the equilibrium constant in order to solve or answer questions about a reaction. So we know what this value is for that chemical reaction. Now, using that information, we're going to take it further. Let's say that the concentrations, the initial concentrations that we have in the system are the following. We have 2 moles per liter of hydrogen, 2 moles per liter of the fluorine, and 2 moles per liter of the hydrogen fluoride. These are the initial concentrations, right? This is where we start. Time equals 0. What do we want to know? We want to tell the future. We want to know what will be the concentration of that hydrogen once the reaction has completed its chemical journey, once it's home, once it's at equilibrium. And we want to know what the concentration of fluorine will be once it gets home, gets to the end of its chemical journey. And we want to know what the concentration of the product will be. So that's our objective. Given this information, the balanced chemical equation, its equilibrium constant, and a set of initial conditions, initial concentrations, calculate what those concentrations will be at equilibrium. So let's look at our 7 steps. Step 1, write the balanced chemical equation. And that's already done. There it is. You have to have a balanced chemical equation. Nothing will work quantitatively if your equation is not balanced. And it is. Step 2, write out the form of the equilibrium constant for this chemical reaction. And that's easy. You can always write out the form of the expression by inspection of the balanced equation. It's going to be equal to concentration of HF to the second power divided by the concentrations of hydrogen and fluorine to the first power. Everybody okay with that?
Why is there 2 stage 2 plus 2 HF?
Well, we have 2 hydrogens on the left. We have to have 2 hydrogens on the right. We have 2 fluorines on the left. We have to have 2 fluorines on the right. We put a 2 in front of the HF to ensure that we have the same number of a given atom on both sides of the equilibrium, on both sides of the reaction arrow. Does that make sense? Yeah. Okay, and what's the value of this guy? We're told 115. So that's step 2. Step 3. Calculate Q. Calculate the reaction quotient. And the purpose for doing this is so we can determine which direction the reaction will have to go to get to equilibrium. So what's Q going to be? It's going to have exactly the same form as the equilibrium constant. The only difference is we're going to plug in the initial concentrations, what we currently have. So what are we going to plug in for HF? 2. We're going to plug in for hydrogen. Also 2 moles per liter. And what are we going to plug in for fluorine? Also 2 moles per liter. So we have 2 squared, 4 over 2 times 2, 4 equal to 1. So which direction must this reaction go? It can only go in one direction, that is the direction towards equilibrium. And Q, okay, Q is less than K, so we don't have enough product, right? You had it right. Since Q is product over reactant, and it's too small, and it's only 1 when it would need to be 115 if it were at equilibrium, we don't have enough product, so the reaction direction is the right. Everybody on the same page? Okay, so now we know which direction it's going to have to go to get to equilibrium, but how far will it go to get to equilibrium? And what will the concentrations of the reactants and products be when we get to equilibrium? And that's what we're going to determine in step 4. Step 4 and 5. In step 4, we're going to create a table, and it's called an ice table, not because it has anything to do with water ice, but I'm going to write the balance equation at the top of the table, and then we're going to have 3 rows. The first row is going to be characterized by the letter I, second row by the letter C, and the last row by the letter E. Now, I stands for initial. All that means is we're going to plug in the initial concentrations of each reactant and product that we start with. So what's the initial concentration of H2? 2. What's the initial concentration of F2? 2. What's the initial concentration of HF? Also 2 moles per liter. So that's the first row in our table, our ice table. Can you see why we call it ice? ICE. The second row, the C stands for change in concentration. What will the change in concentration be for the hydrogen in order for the system to get to equilibrium? Will hydrogen be consumed or will hydrogen be formed as the reaction proceeds towards equilibrium? Which direction is the reaction going? Towards products. So hydrogen is going to get consumed, right? So how much? We say negative X moles per liter of hydrogen will be consumed in order to get to equilibrium. The minus is indicating that that component is getting used up, being consumed as the reaction proceeds, and X is the number of moles per liter of that do get consumed. We don't know what it is yet. What will the change in concentration of fluorine be? Notice stoichiometric coefficient of 1 here, stoichiometric coefficient of 1 there. The fluorine is going to be consumed as well, right? At the same level, minus X moles per liter of fluorine will have to be consumed to get to equilibrium. Now we go across the pond, and here we are on the product side. What will the change in concentration of product have to be to get to equilibrium? It's going to be positive. Positive what? What's that? 2X. Does that make sense? If X moles per liter of hydrogen are consumed, how much HF has to be formed? 2 times X moles per liter. What if this X were 1 mole per liter? 1 mole per liter of hydrogen consumed would form 2 moles of liter of HF, right? So X moles per liter of hydrogen consumed means 2 times X. We're just looking at the stoichiometric coefficients. They tell us that information. Why is it positive? Because the reaction is moving in the product direction from left to right. We're consuming reactants, we're producing product. Now, the last line stands for equilibrium. E means equilibrium concentration. So we're going to write the equilibrium concentration of each reactant and product into this table. And the equilibrium concentration of hydrogen will be 2 moles per liter where it started, plus the change in its concentration that had to occur to get to equilibrium. So it's going to be 2 minus X moles per liter, 2 moles per liter minus those X moles per liter that had to be consumed to get to equilibrium. What will the equilibrium concentration of the F2 be? Same thing, 2, where we started, plus the change in concentration that had to occur to get to equilibrium. What about the HF? What's the change in concentration of HF that has to occur to get to equilibrium? It's going to be 2, where we started, plus the change in the concentration that had to occur to get to equilibrium. And that's our completed table. And we have each concentration, H2, F2, and HF expressed in terms of this unknown variable X. If we could find X, we can tell you the concentration of each one of these, right? Because hydrogen is 2 minus that X value. F concentration, F2 concentration, 2 minus the value of that X. And the concentration of HF at equilibrium will be 2 plus 2 times that X value. But how do we find the value of X? We plug these equilibrium concentrations. These are the equilibrium concentrations expressed in terms of this unknown variable X. We plug them into, that'll be step 5. We plug them into the equilibrium constant expression. There's our equilibrium constant expression. Here are our concentrations at equilibrium. So we're going to plug in the HF. That would be 2 plus 2x. That's the concentration of HF. Do we do anything else to it? What do we have to do to the concentration of HF? We have to square it. This is the concentration of HF at equilibrium expressed in terms of this X variable. So we have to square that. And then we divide through by the concentration of hydrogen. Look at our table, that's 2 minus X. And divide through by the concentration of HF, F2, the fluorine molecule, and that's also 2 minus X. And what must that ratio be equal to? So we have one equation with one unknown, X. Now you do a little algebra, and we'll find X. And we can determine each of these concentrations. So notice this is two minus X times 2 minus X is 2 minus X squared. So we have 2 plus 2X squared over 2 minus X squared is equal to 115. We could say 2 plus 2x over 2 minus x. Take the square root of both sides. You get that. And now you solve for x. And x is equal to, what could I get for that? 1.53. X is equal to 1.53 molar. everyone okay with this step 5? What we did is took these equilibrium concentrations expressed in terms of that unknown variable X and plugged them directly into our equilibrium expression, whose value we know. And then we solve for that X term, and it's 1.53. Therefore, now we can calculate the concentration of each reactant and product by just plugging in X.
What happens in the stuff where it's the square root of 1 into the 2?
I'm
Like,
sorry.
there's 2 plus 2x and then there's 2 minus it. What happens to the 2 and the, like? So I know you square root it, this step before, but,
Well, we have 2 plus 2x squared
right.
over 2 minus x
I know
squared.
you square root both sides.
Yeah, take the square root of both sides, and that gives you this.
I think you mean like the 2 and then 2 divided, cancel out, and then it was 2
There's so
over,
many.
2x over negative x.
Oh, okay, no, I see. So.
And I think the square root of 115 is like 10.7, and now you just solve for x. It's good to ask questions like that. If you're not the only one who probably like, wait, where did that go? Or where did that come from? We just took 2 plus 2x squared over 2 minus x and 2 minus x. That's this term, 2 plus 2x squared over 2 minus x squared. Take the square root of both sides. That means take the square root of this, square root of that, square root of that, and now solve for x. And get 1.53. So what's the concentration of hydrogen? Once this chemical reaction has gotten to the end of its chemical journey, it's home, it's at equilibrium, it's where it wants to be, the concentration of hydrogen will be 2 minus X. 2 moles per liter minus 1.53 gives 0.47 moles per liter. Concentration of fluorine is going to be 2 moles per liter minus the X value, 1.53 is 0.47 moles per liter. HF, its concentration is going to be 2, where we started, plus 2x. So that will be 2 plus 2 times 1.53. And we do the arithmetic there, and we get 5.06 moles per liter. And that's what we were looking for. Yes.
Is that the concentration at equilibrium or is that one?
These are the concentrations at equilibrium. That's what these are. Remember that E on that, in that table,
Yeah.
this is saying the equilibrium concentration for each reactant product.
I didn't use that. I just making sure.
Yeah.
Making sure it-
Okay, we're going to do another one. Very similar to this. Any questions on any other step in this calculation? I think it's amazing that you can know this, right? And the reason we can do this is because of the reliability, the dependability of the equilibrium constant for a given chemical reaction. Once it's achieved equilibrium, that value has to be that for this chemical reaction at that temperature. And therefore, that's a take it to the bank. You can trust it, you can count on it, and therefore we can do these kinds of calculations, knowing that that is got to be the value of these ratios of concentrations at equilibrium. All right, so now let's do a similar problem using the same chemical reaction at the same temperature, and therefore it's going to have the same K value, but now we're going to have a different set of initial concentrations of hydrogen and fluorine and hydrogen fluoride. let's say that our initial concentration of hydrogen is 1.0 moles per liter. Our initial concentration of fluorine is 2.0 moles per liter. And our initial concentration of our product, hydrogen fluoride, is 0 moles per liter. So this is where we are. We've gone into a lab and we've mixed 1 mole per liter of hydrogen with 2 moles per liter of fluorine gas. And we're going to let the reaction go. And we want to know what are the concentrations of reactants and products once this reaction gets home, once it gets done with its chemical journey. So step 1, balance the equation. It's already done. Step 2, write out the form of the equilibrium constant with its value, already done. Step 3, determine Q. You don't even have to do a calculation here. What must Q be? 0. Good, because what is Q? Product concentrations over reactant concentrations, the initial concentrations. And what are the what's the concentration of the product? 0. What is any number divided by what is 0? 0 divided by anything is going to be 0. So
That's some of our algorithm. It's really difficult, depends on the
I'm sorry.
Does that not mess up our algorithm when we do the ice table?
Oh, it won't be in the ice table. You'll see. Why do we calculate Q? We calculate Q for one reason, to determine which direction the reaction is going to go. Not where it will be once it gets to the end of its journey, but which direction it will go to get to the equilibrium state. So which direction must it go? You have to determine the relationship between K and Q. K is 115, Q is 0. Q is too small. What do we not have enough of? Products, right? If Q is less than K, we don't have enough product. Remember that the Q and K are product concentrations over reactant. If this is too small, it's because we don't have enough product. So how can you make more product? Run the reaction in the forward direction. So the reaction direction will be towards product. Right? Anytime Q is equal to 0, the reaction can only go one way, towards product, because all we have is reactant. We don't have any product that can make the reaction go in reverse. So step 4. Now we know which direction the reaction is going to go, so now we create our ice table. What does I stand for? Initial concentrations. What's the initial concentration of hydrogen? 1.0 mole per liter. What's the initial concentration of fluorine? 2 moles per liter. What's the initial concentration of hydrogen fluoride? 0. Okay. What does the C stand for? The changes in concentrations that have to occur for the system to get to equilibrium. So what is the change in hydrogen going to be? Is hydrogen concentration going to decrease as it moves towards equilibrium or increase? It has to decrease, right? Because it's going towards product, so we're going to have to consume hydrogen. How much hydrogen is going to be consumed? X moles per liter.
Is it okay way to think about it, like, for specifically the ice table, whether or not the part that we're looking at is an input or output? Because when you say products and reactants, I think that this talked about this in the book too. It said, oh, well, by the way, reactions can go both ways, but we talk about products and reactants like they're going one way or the other. So is it a good way to think about it, like if it's an input, you're going to be negative, and if it's an output of the reaction, it's going to be positive versus part of the reaction?
I wouldn't think that's a good way, but if it works for you and you're getting the right answers, then that's fine. To me, it's more physically accurate to say that, the reaction is moving towards the product, so we're reducing the concentrations of our reactants. That's a more physically descriptive description of what is literally happening.
Yeah.
But if you like the idea of inputs and outputs, and
Well,
it means the same thing.
Yeah, because it's.
Just a different way of saying the same
Yeah.
thing. And if you get the right answers, fine.
Right.
Okay, so what is the change in concentration for the F2? Negative X. That means that X moles per liter of the fluorine has to be consumed for the system to get home, to get to equilibrium. The minus is telling us it's being consumed. The X is the quantity, the amount in moles per liter of that component that has to be consumed. And what do we put for the change in concentration of HF? 2X, right? The change would be 0 where it started, plus the change that had to occur to get the equilibrium. Well, change is 2X. If X moles per liter of hydrogen are consumed, 2X moles per liter of HF are formed. How do we know that? Based upon the stoichiometric coefficients, the 1-to-2 ratio. For every mole of hydrogen reacted, you get 2 moles of HF. So if X moles per liter of hydrogen are reacted, we're going to get 2X moles per liter of HF. Okay. What are the equilibrium concentrations? That's row 3. It's going to be where we start, plus the change that had to occur to get to equilibrium. For hydrogen, it's 1 minus X. For fluorine, 2 minus X. And for HF, it's 2X. So these are literally the equilibrium concentrations of hydrogen, fluorine, and hydrogen fluoride, expressed in terms of an unknown variable that we call X. All we have to do now is to find what X is. And how do we do that? By taking these equilibrium concentrations and plugging them into the equilibrium constant. So that's step 5. We're going to take these equilibrium concentrations expressed in terms of X and plug them directly into the equilibrium constant expression. So we have concentration of HF, it's 2X. Don't forget the square. Divided by the concentration of H2, which is 1 minus X. And divided by the concentration of fluorine, F2, which is 2 minus X. And what must the ratio of those terms be equal to?
115.
115. So now we have to do some algebra. 2x squared is 4x squared. And now if you oops, on one. Make sure I got these right. Yep. And so now you multiply out that denominator, and we're going to get 2 minus 3x plus x squared. Right, just by factoring that, not factoring it, by multiplying out that denominator. Okay. Now we got to solve for x, and you get this. This is that equation expressed in terms of x. And what kind of equation is this? Quadratic equation. It's quadratic because it has an x squared term And how do you solve the quadratic equation? You use the quadratic formula.
We can factor,
Beg your pardon?
you can factor it instead of each chunk equals 0.
So we're gonna,
Sometimes it doesn't have that.
what is the quadratic formula? Quadratic formula says that x is going to be equal to minus b plus or minus the square root of b squared minus 4 times a times c, all of that divided by 2 times a. So what are these a, b, and c terms? A is the coefficient of our x squared term. B is the coefficient of our x term. And C is our constant. So A is equal to 111, B is equal to negative 345. It's so easy to drop a negative in the quadratic equation. Don't drop any of the signs. And C is equal to 230. Is that right? Yes. Okay. So now you plug and chug. Plug in A, 111, plug in B, minus 345, plug in C, 230, do the arithmetic. And you get how many values for x? 2. Every quadratic formula, every quadratic equation will have 2 values of x that make it true. In this case, one of the x values is 2.14 and the other is 0.97. So both of these will make this equation true. 111x squared minus 345x plus 230 equals 0. Both of those work. But only one of those is appropriate for our problem. Only one is physically possible. And that'll always be the case in any problem I give you. You'll get 2 possible values, but one of them will be physically impossible. Which one can we eliminate as a possibility? What is the equilibrium concentration of hydrogen? 1 minus x. What if x were 2.14? What would we get? We get a negative concentration. There's no such thing as a negative concentration. You can have a negative change in concentration, but you can't have a negative concentration. That would be like having a negative height or a negative weight. Doesn't exist. So we can, that just doesn't make any physical sense. So we're left with this one. And now we can calculate concentration of each of our reactants and products at equilibrium. These were our initial concentrations, and these are now going to be at equilibrium concentrations. H2 is going to be 1 minus x. And that would be 1.0 minus 0.97 is going to be 0.03 mole per liter. Fluorine's equilibrium concentration, 2 minus x, 2.0 minus 0.97, which is 1.03 mole per liter. And HF at equilibrium. Look at our table. That's the equilibrium concentration, 2 times x. And that will be 2 times 0.97, which is going to be equal to 1.94. And that would be the answer to the question. What are the concentrations, the equilibrium concentrations of our reactants and products for this chemical system? Once it gets to the end of its chemical journey, once it gets home, once it gets to equilibrium. And, yeah. But how many steps are there in our 7? We've done 6. We haven't done step 7. And step 7 is a way to check to make sure you didn't make any mistakes. And how likely is it that you make a mistake in the quadratic equation?
Right.
There's a good probability, right? Because you have all those changes and signs, and it's easy to make a mistake. So when you get done, you do a check. And what is check? The check, step 7, is simply taking the equilibrium concentrations that you calculated based on this approach and plugging them back into the equilibrium constant expression. So K is equal to F squared 2 over F2. We'll plug in these concentrations that we just calculated based upon our steps 1 through 6. HF squared, we have 1.94 squared divided by H2, 0.03 divided by F2 concentration, and that's 1.03. And do the appropriate number crunching. And we get a value of 121. So what do you think? You think we have to retool and start all over again? Did we make a mistake? No, that's rounding errors. And if you dropped a sign here, or if you got a number wrong in here, your calculated check equilibrium constant value will be nowhere near the true value. You might have 20 million here, or 10 to the negative 12, or some ridiculous number, and you know you're wrong. If you're anywhere near what the known equilibrium constant is, within, let's say, 5 or 10% of what the true value is, you can assume you've done everything correctly. And any differences are probably due to rounding errors. I shouldn't call them errors, down to rounding significant digits and things like that. Okay. Questions? Concerns? So the assignment. How'd you get one of those, Bo? How did you get one of those?
You put it on YouTube.
Oh, that's right. You're ahead of the game. This is what you're going to turn in next week. Notice that right at the top, it says your submission must be unique, must be legible, and clear explanations where explanations are requested. So make sure to follow those guidelines precisely. There are 8 questions. Provide explanations. They're requested. Do the calculations. And then select this next. And it's worth 25 points. That's the same value as a full lab report. It's open book, open note, open friend. I encourage you to sit down and talk with other people while you're doing it. Share ideas, learn from one another, teach one another. It's the best way to learn. So that's it. Thanks for your attention.